All right, so today in Algebra 2, we're going to look at our test review for 6.1 to 6.3. So 1 through 6, the directions say evaluate, round answers to the nearest hundredth when necessary. Okay. So evaluate, remember anytime you see the word evaluate, that means you're going to have a number for an answer. So number 1, log base 5 of 1. So remember this is saying 5 to what power equals 1, right? 5 to what power equals 1? Anything to the 0 power equals 1, so this is equal to 0. This one, number 2, log base 6 of 36, saying 6 to what power equals 36? Well, I know that's 6 squared, so that's 2. Number 3, log base 1/2 of 32. So 1/2 to what power equals 32? I know I'm starting with a fraction and I'm getting a whole number, so I know it's going to be a negative number. So 2 to the 5th power equals 32. So 1/2 to the negative 5th equals 32. Number 4, log base 4 of negative 28. 4 to what power gives me negative 28? Okay, well, I don't know that. And also, look, negative, remember, you cannot take the log of a negative number, so this one is undefined. Remember that, no logs of negative numbers. Number 5, the natural log of 32, okay? Again, this would be like saying e to what power equals 32? We don't know, that's not going to give us a nice whole number, so this is where we use the calculator. So in our calculator, we type in natural log of 32, and we get, let's see, to the nearest hundredth, so that's 2 decimal places, 3.47. Number 6, log of 18, so 10 to what power is equal to 18? Again, that's not going to be a nice whole number, and since it's an LOG log, we can type that in our calculator, so log 18, 1.23. All right, so we evaluated our logarithms. Just remember, evaluate means you need a number for an answer. All right, so now we're going to look at 7 and 8, graphing logarithms. So number 7 says y equals 2/3 to the x power, all that minus 2. We can go ahead and start with our domain, range, and all of these things. Okay, so remember domain of all our exponentials, all real numbers, negative infinity to infinity. The range, remember that this number down here, the k value, affects the range. Remember that all exponentials start with a range of y greater than 0, but this one shifted down 2, so now my range is going to be y is greater than negative 2, or I could say negative 2 to infinity. Is it a growth or a decay? Well, it's 2/3 is the number that's being raised to an exponent. 2/3, that is a fraction between 0 and 1, so this is a decay. And then my asymptote, okay, again, that k value is my asymptote. So my asymptote, y equals negative 2. So I can go ahead and make me an xy table. Again, I'm plugging in negative 2, negative 1, 0, 1, and 2. Go ahead and put my asymptote on my graph, dotted line. Let's see, if we plug in 0, that's the easy one. 2/3 to the 0 power, anything to the 0 power is 1. 1 minus 2 is negative 1. If I plug in negative 2, okay, so then that means I flip this and square it, so I would get 9/4 minus 2, so minus 8/4, so I would get 1/4 there. Plug in negative 1, so that means 3/2 minus 2, so 3/2 minus 4/2 gets me negative 1/2. I plug in 1, so I'm at 2/3 minus 2, so 3 times minus 6, so 2 minus 6, negative 4/3. And then if I plug in 2, so 2/3 squared, so that's going to get me 4/9 minus 2, so 4 minus 18, negative 14/9. So that's what I'm going to graph. 0, negative 1, negative 1 up, negative 1/2, negative 2 1/4, negative 1, negative 1 1/4. And so it's getting close to my asymptote, but it's not going to touch it as fast. So there's my graph. And again, by looking at my graph, I can tell that it is in fact a decay function, because from left to right it is decreasing. So Now number 8, graph y equals 3 times 2/3 to the x power. Again, my domain, this is all real numbers. It's an exponential. My range, I don't have a number being added or subtracted, so my range, y is greater than 0. This is another decay function because the number inside parentheses is 2/3, and my asymptote here is y equals 0. So again, I could go ahead, do my asymptote dotted line, make an xy table, -2, -1, 0, 1, and 2. Again, the 0 is the easy one to plug in. 2/3 to the 0 power is 1. 1 times 3 is 3. I plug in -2. I have to flip 3 halves and square it. So then I have 3 times 9/4, which is 27/4. So this is 27/4. If I plug in -1, that's 3 times 3 halves. So that's 9 halves. If I plug in +1, that's 3 times 2/3, which is simply 2 because my 3's cancel. I plug in 2, so that's 2/3 squared, so 3 times 4/9. That goes into there 3 times, so I get 4/3. Right. So let's go ahead and graph these. So over 0 up 3. Over 1 up 2, over 2 up 1 1/3, -1 up 4.5. My -2 is way up here. So again, I can see that it's going to get close to this asymptote, but it's not going to touch it or cross it. And again, by graphing it, I can tell that it is indeed a decay function because from left to right, it is decreasing. And number 9. You deposit $1,500 in an account that pays 2.5% annual interest compounded continuously. What is the balance after 3 years? So my principal, my initial investment, $1,500. My interest rate is 2.5, but as a decimal, 0.025. Continuously, okay? Time is 3 years. So this is the function, or the equation, A equals P times E to the RT power. Anytime they say continuously, this is the equation that we use. So we just want to plug everything in here. So A equals 1,500 E to the 0.025 times 3. So 1,500. If I multiply 0.025 times 3, I get 0.075. So I'm going to type this in my calculator, 1,500 times e to the 0.075. Round appropriately. Remember that this is money, so I need a dollar sign. So I get $1,616.83. I always round 2 decimal places with money. Let's look at number 10. You deposit $3,250 in an account, so my principal is $3,250. My interest rate, 3% as a decimal, 0.03. Compounded monthly, so my N here is 12. What's the balance after 7 years? So T equals 7. So on this one, A equals P times 1 plus R divided by N to the NT. That's the equation that we'll use. Should have these equations memorized. All right, so I get A equals 3,250. 1 plus 0.03 divided by 12, all of that to the 12 times 7. So the very first thing I want to do is 0.03 divided by 12, and then add that to 1. So inside parentheses, I get 1.0025, and then 12 times 7 gets us 84. And so now I can type this in my calculator. And dollar signs. So 1.0025 to the 84th power. All that times 3,250, we get $4,008.40. Number 11, you invest $1,200 in a bond that decreases at a 1.75% per year. What is the value of the stock after 5 years? Round appropriately. this is y equals ab to the x. Okay? Growth and decay. It decreases, so this is a decay, so my b is going to be 1 minus, okay, my rate was 1.75, but I have to put that as a decimal, so 0.0175. So 1 minus 0.0175, that's going to get us our b. When we do that, we get that b is 0.9825. So let's plug this in. Y equals a, that's what we started out with, 1200, times our b, our decay factor, 0.9825, to the t power, they tell me 5 years, so to the 5th. And again, it's going to be money. So 0.9825 to the 5th power times 1200, and we're going to get $1,098.61. We know that our answer makes sense because since they told me that it was decreasing, I knew that my answer had to be smaller than what I started out with, 1200, and it is in fact smaller. Number 12, you invest $13,200 in a sculpture that increases in value. So this is an exponential growth by 6% each year. So here my rate is 6 as a decimal 0.06. So this time my B is my growth factor. I add 1 to it. So 1 plus 0.06 gets us 1.06. So Y equals the initial value, 13,200. The growth rate, 1.06, to how many years? 20 years, so to the 20th power. So there's our equation. So here, 1.06 to the 20th, and then times 13,200. So after 20 years, our sculpture is worth $42,334.19. That increased. Number 13, the squirrel population of Joplin, Missouri was 179,000 in 2015. It is expected to decrease by about 4.6% per year. Write an exponential decay function, P of t, and use it to approximate the population 2042. So here I have two separate problems. Okay, first I have to write the equation, and then I have to plug everything into that equation and find the population in 2042. So the very first thing I need to find is my decay factor. So remember that our B, our decay factor, is 1 minus 0.046 in this case. So when I do 1 minus 0.046, I find out that my decay factor is 0.954. So my decay function is going to be P of t equals the initial population, 179,000, times my decay factor, 0.954, to the t power. So now we're going to use that to find out what was the population in 2042. So I just have to find out how much time between 2042 and 2015. So subtract 2015 from 2042, and we get that was 27 years. So our t is 27. This, again, the equation itself was the first part of the problem. Now we're going to take that and we're going to plug in 27 to that t and find that the population was approximately, okay, and again it says approximate the population. We want whole numbers here, so we're going to round this to approximately 50,195. Let's see, our units are squirrels. So in 2042, Joplin, Missouri will have approximately 50,195 squirrels. And number 14, write an exponential model given the 2 points, 5 comma 28 and 6 comma 47. Remember that I can write an exponential model. Again, this is going to be the y equals a times b to the x power. I need to find my b, that is the rate, since these go up by 1 in x value from 5 to 6. To find my b, it's the ratio of my y values, so 47 divided by 28. So 47 divided by 28, b is approximately And we're going to round here to just like 3 decimal places. So I would get approximately 1.679. So now that I have B, I need to find A. I pick one of these points. I'm just going to pick the point 5, 28. And I plug into this equation, and I'm going to solve for A. So instead of Y, I'm going to plug in 28 equals A. That's what we're looking for. B, we just found 1.679 to the x power. The x value that I'm using is 5. So when I solve this, I find out that A is approximately 2.1. Therefore, my equation, y equals 2.1 times 1.679 to the x power. There's my exponential model. All right, last page, solving logarithms. So it says solve, round your answers to the nearest hundredth when necessary, and check. Remember, if you start out with a logarithm, you must check your answer. Okay? So number 15, log of 3x minus 2 equals 2. Remember that in order to solve a logarithm, I change it to an exponential. So my little shortcut, log, I don't have a base, so it's understood to be base 10. So this is really 10 squared equals 3x minus 2. 10 squared, that's 100. What's 3x minus 2? Add 2 to both sides, so I have 102 equals 3x, and divide by 3, so I get x is equal to 34. But before I circle that, say yes, that's my answer, I need to check it. So over here, I'm going to check, because I started out with a logarithm. So log of 3 times 34 minus 2, does that equal 2? So 3 times 34, and then that's, let's see, 102 minus 2, so this becomes log of 100 equals 2. Is log of 100 equal to 2? Yes, it is. That checks. So 34 is our answer. Number 16, the natural log of 2x plus 3 equals 4. Again, change to an exponential, but this time, since it's a natural log, my exponent is, sorry, my base is e, so it's e to the 4th equals 2x plus 3. I need to get x by itself, so subtract 3 from both sides. So I get e to the 4th minus 3 equals 2x, divide by 2. So x is approximately, remember we're not going to round to the very end, so e to the 4th, subtract 3, and then divide by 2. And they tell me round to the nearest hundredth, so 2 decimal places, so x is approximately 25.80. And to check my answer, because I started out with a logarithm, so ln of 2 times 25.8 plus 3 equals 4. So I get the natural log of 54.6 is equal to 4. I can type that in my calculator to check that. And I just have to remember that I'm not going to get this exact number of 4 because this has been rounded. And so, yes, this checks out. X is approximately 25.8. Number 17, 10 to the x minus 4 equals 64. Well, I can see that this is not going to be a nice whole number. 10 to what power equals 64? It's not a nice whole number. So when that's the case, we start out with exponential. We take the log of both sides. So I'm going to say the log of 10 to the x minus 4 equals the log of 64. Log of 10, remember this, is equal to 1 because they have the same base. So then all I have on this side is x minus 4 equals log 64. So x is going to equal the log of 64, all of that plus 4. So when I type that in my calculator, the log of 64 equals, add 4 to it, I get x is approximately 5.81. I do not have to check this one since I did not start out with logarithms, but I can check it if I would like to check to make sure I got the correct answer. And our last one, number 18, 1.7 e to the x equals 73. I'm trying to get e by itself, so divide everything. So when I divide both sides by 1.7, So now I have e to the x equals 42.94117647. And again, remember, we do not round until the very, very end. Okay, this is not going to be a nice whole number. So again, I do the log of both sides. But since I have an e, I have to use the natural log. So I say the natural log of e to the x equals the natural log of 42.94117647. Natural log of e, again, that's 1. So I get x is equal to the natural log of 42.94117647. I'm going to plug that in my calculator and find that x is approximately 3.76. Again, I am not required to check my answer because I did not start out with a logarithm, but I can plug it in just to make sure that I did get the correct answer. All right, so that is our test review for sections 6.1, 6.2, and 6.3. So just make sure that you know how to do all of these, know your equations, know how to find your growth factor, your decay factor, know all of the equations for continuously compounding interest and compounding interest formulas, know how to graph, domain, range, and you should be good to take the test.